In assembly language, we manipulate the address, the position in memory, of data.
For example, a label can be a location for a value, and to operate on data, we must load the values into registers.
We also have seen that an address is a position of program code where the execution can jump and resume from such address.
A compelling aspect of the von Neumann architecture, where data and programs share the same memory, is that we can operate with addresses of data and programs.
With this power also, there are risks, and a program may accidentally modify code as if it were data.
In high-level programming languages, operating and using addresses in memory is also a common practice to build large data structures and allocate and use memory dynamically, as the program may require during its execution.
Pointers provide the most basic form for this in C.
Pointers in C are also memory addresses, but at least they indicate the type of data that is meant to be held at the address indicated by the pointer.
Like many types-related aspects, the programmer has excessive freedom in mixing data types in C.
Other programming languages are more strongly typed, meaning that mixing expressions and assignments with different data types is excluded unless explicit casting is used.
Consider the following example, where V is a global array of integers, thus, initialized with 0 values.
We can confirm that the value of the first element is 0.
However, we can also declare a variable p1 as a pointer to an integer and store the address of the first element of the array in p1.
In C, the ampersand symbol is used to obtain the address of a variable, not its value.
We thus notice that the address of an array, or its base address, is the same as the address of its first element.
To get the value indicated by a pointer, C uses the asterisk.
This use of the asterisk is called dereferencing.
We can check that following P1, we have the value 0, which is the value of the first element in the array.
Notice that C is not strongly typed in that a pointer to an integer can be mixed with a pointer to an array of integers.
Although, the GCC compiler raises a warning for mixing these types.
In this example, P2 has been declared a pointer to a pointer to integer.
Thus it can hold the address of a pointer to an integer.
We can copy an address as the value of this P2 pointer.
The address that we copy is the location of pointer P1.
We can confirm that the double dereferencing obtains the value of the first element of the array.
Using ampersand to obtain the address and end dereferencing are inverse operations.
Pointers are useful for scanning over an array without the need to perform index arithmetic.
That is, it is less costly to keep the position of the element we are interested in the current iteration within a loop than computing the position from an index variable.
Consider, for example, the following C code that adds the elements of an array.
The pointer version of the scan seems particularly succinct.
Notice that these are the two versions we indicated in the previous video, for implementing a loop when the array does not hold bytes but a larger data type.
In the explicit index form, the formula for finding the position of the requested ith item must be computed in each iteration.
Those calculations add to the amount of work in each iteration, resulting in a more time-consuming loop.
The pointer version only has to update the address by incrementing it by the size of the items in the array.
This difference in computation in loops is even more evident with matrices, or b-dimensional arrays.
Such arrays are stored in memory linearly, called row major order.
Row major order means contiguous space for the items of the b-dimensional array, one row at a time.
The storage strategy means that the second index varies more rapidly.
Alternatively, the first index designates the row, thus, all items with a common first index are adjacent.
The address of the ith element of an array has a displacement from the base address of the b-dimensional array that is as many rows by the length of a column, plus the displacement in the column.
And this displacement must account for the size in bytes of the array items.
Since the formula for a specific item of a matrix implies sums and multiplications, it should not be surprising that if a loop is going to access all the elements of a b-dimensional array, to implement this with pointer arithmetic is much more efficient.
Pointer arithmetic only needs to increment the scanning pointer by the size in bytes of the items in the array.
These efficiencies are crucial in current algorithms, but also may make you wonder if intensive arithmetic calculations with matrices could be performed even faster.
You may want to explore the topics that have gained tremendous interest, such as deep learning and, in particular, the training of convolutional neural networks with GPUs, or graphics processing units.
The massive amount of work required for training such machine learning models profits from the parallelization as well as the better memory bandwidth of GPUs over the traditional CPUs under a von Neumann architecture.